I think where we had left off, it says the diagram shows the graph of f double prime of x. So from this graph, f double prime of x, I'm going to label this point C. We know on this side it's positive, on this side it's negative, which would mean this section of your original graph is concave down. This part of your original graph is concave up. With that in mind, we also find out from this that, I'm going to draw another one, f double prime of x. I'm going to label it like this. If this section is negative and this section is positive, and you wanted to go back just one graph, that would be like going from the derivative to the original graph. When you're going back just one graph, you tell where things are increasing and decreasing. So if f double prime of x is negative here and positive here, which means on the original it's concave down and concave up, if you used f double prime for f prime of x, would it make sense that f prime of x is decreasing and then increasing? And so for f prime of x, C will be a minimum. So we can take some place for C to be a minimum and decreasing, then increasing. And this is where our final graph can differ based on what we decide here. Because I could have put this minimum point for C basically anywhere. I could have had this whole parabola shifted up as opposed to shifted down. So my original graph of f of x could be different depending on where I decide I'm going to draw my parabola for f prime of x. And that would be taken into consideration for a question like this. And the reason for that is because when you're working up, there could always be a constant that when you take the derivative goes away. Does that make sense? Like the derivative of x squared minus 4 is 2x, is the same derivative for x squared plus 1,000. The derivative is 2x. Can you see that x squared minus 4 is a parabola moved down? And x squared plus 1,000 is a parabola way moved up. They're the same graph, but in very different places. So in this situation, the fact that I know f double prime of x as a line lets me work backwards and say that my derivative graph would have to be a parabola for my second derivative to be a line, but I don't know where that parabola is. Based on where I drew that parabola, though, I can now make a number line for f prime of x. I'm going to call this point x1 and this point x2. That would be x1 and x2. And taking that into consideration, I know that my second derivative is positive here, my first derivative is positive there, negative there, and positive here. What does that tell me about my original graph? It has to go in this direction. And so I'm going to have a maximum at x1, a minimum at x2, an inflection point somewhere at C, concave down, concave up, purple one is f of x, and the blue one f prime of x. So we really use our number lines because they tell us lots of information. And we have to realize that our second derivative, even though we normally for curve sketching would say that it's all about concavity, when working backwards, your second derivative also tells you stuff about your first derivative, about where it's increasing and decreasing, and where a maximum or minimum of your first derivative would be. So we can find out at the point C that C is going to be a minimum point of our first derivative. This kind of thinking, being able to bounce back and forth between your number lines and what they mean, is very typical of what the IB exam likes to do. Today, we're going to do some graphing from beginning to end. And that's important because they want you to know all of the steps that you need to do to graph something completely. But more typically, in a question, what they're going to do is they're going to say, hey, I started you off in the first derivative. What can you tell me? What can you tell me about the second derivative? Or here's something about the second derivative. What does that tell us about the point? Is it a maximum? Is it a minimum? Do you have enough information? And so here we have our next example is very much like that. The following diagram shows part of the diagram of f of x. We have a local maximum at A where x is -2, a local minimum at B where x is equal to 6. Let's sketch the graph of the derivative. So if I do my number line for my derivative, right, here's f prime of x, I would know that at point A and point B, that's where my derivative would equal 0, because that's where I have a maximum and a minimum. I know from the graph that my original graph is increasing, then decreasing, then increasing. So that tells me my derivative had to have been positive, then negative, then positive. So when graphing our derivative, I would go to point A, make it 0. Go to point B, make it 0. Know that it has to be positive here, negative in between, and positive afterwards. So knowing what your maximums and minimums create your derivative to equal 0, very important. Then your sign diagram tells you where it's positive and negative. And when we talk about positive and negative, those are your y values, right? Like in between A and B, those are the points where it's 0, it's negative, that means your y values are negative. And then here in part B is the application question. Without graphing things completely, which of these are, do you know? Which of them don't you know? Okay? Do we know the exact value of f of 0? Is there any scale given? No. What can you tell me about f of 0? It's bigger than 0. Is it all right if I put a plus sign underneath there to say that it's positive? Do we know the exact value of f prime of 6? We drew f prime at 6. Yes, we know that that one is exactly 0. Do we know, we don't even have the second derivative graph at all. How can we figure out the value or some sort of inference about the value of f double prime of -2? Well, if I go to f at -2, my original graph is concave down. So I know that here it's concave down. What would have to happen for it to be concave down? It would have to be negative. So as far as listing these from least to greatest, we would know that f double prime of -2 is least,
f prime at 6 would be second at 0, and f of 0 would be the greatest because it's positive. So again, not actually finding the answers, but taking the information from the graph. And in order to find the purple part, you would be thinking about, right, if I draw a number line for my second derivative, I would know possibly at 2 is where it changes from concave down to concave up. Concave down means it's negative, concave up means it's positive. So at -2, it falls into that negative section. So these number lines are great tools not only for graphing, but also for analyzing what's happening. So summary of everything we've done so far. If you are curve sketching, first of all, find your intercepts if possible. Y-intercept you can almost always find without a calculator. Sometimes your x-intercepts you can find with factoring. Sometimes you wouldn't be able to find them other than with a graphing calculator. Also, along with intercepts, look if there are any asymptotes. Those would be non-permissible values for your vertical asymptotes. And for horizontal asymptotes, if the degree is the same on the top and the bottom, and imagine it as you're getting, x is getting very, very big. Like imagine throwing in 100, throwing in 1,000, throwing in 1,000,000. Does it get close to something? Does it get close to 0? Or does it just keep getting bigger? If it keeps getting bigger, you will have no horizontal asymptote. But if it goes to 0, or if it goes to some value, like it gets close to 2, draw your asymptotes as well. This, 1 and 2, is sort of stuff we've done in grade 12 pre-calculus. Then we get into our calculus parts. We use our first derivative to find our stationary points and our inflectionary points. Okay? And what I mean, we use the first derivative to find our stationary points, and we use our second derivative to find our inflection points. Now, I would draw my number line for f prime of x to find my max and min, or you could use the second derivative to find my max and min. I would draw my number line for my second derivative to find concave up and concave down. Right? When you do your first derivative, you will automatically find out where things are increasing and decreasing. And by finding where things are increasing and decreasing, you can use your first derivative test to say, oh, that's a maximum, or oh, that's a minimum. Then drawing your number line for your second derivative. You've got concave up happy, concave down. Remember that when you find a maximum, a minimum, or an inflection point, you find the x coordinate from the first derivative, x coordinate from the second derivative, but then to find the y coordinate, you always plug in back to the original equation. So, what we are going to do is we are going to get into groups to do the following graphs.